started in Smite. So what is Smite? In Silicon Valley terms, Smite is a trust and safety platform for the internet. But seriously, what does Smite do exactly? So Smite is helping customers detecting all kinds of bad behaviors and bad actors on the internet. For example, we can help marketplace websites to detect fraud, credit card transaction fraud, such as chargebacks, as well as spam messages. And we can also detect spam and harassment messages on social websites. And for things like crowdfunding sites, we can help them detect things like fake campaigns that a scam try to trick their customer to donate. So we can detect all kinds of bad behaviors so that we can take care of the trust and safety side of the business so that our customers can focus on their core product experience. And it turns out that to do all these interesting, exciting things, the centerpiece of our infrastructure is about counting, which is all this talk about. So what do I mean by that? To do all this detection, Smite needs to answer a few very simple questions. For example, for a given IP, how much activities have we seen so far for the IP? Or more specifically, how many requests have we received for that from that IP in the last hour or last minute? Right? To make it more interesting, what if the IP is IPv6, which has much larger space? Or if we know a particular request is for a sign-up for a website, then we want to know how many sign-ups has happened from a single IP in the last hour. Even more specifically, if the sign-up involves the email address, then we can extract the email domain and ask how many unique emails have we received for the sign-up from this IP for a particular domain, from which we can tell if someone is automating a fraud campaign that tries to build and create a lot of fake accounts at the same time. Similarly, we can also create accounts for people who are sending a lot of messages that are very similar to each other, which we'll use as a feature and a signal for detecting spam messages. So this is one type of counting problem. There's another type of counting which I won't be talking about in this talk in detail, but I want to mention here, which is to do unique counts for a particular actor that requires its own set of algorithms. And that later I'll show that can be built with the same principle, but I won't cover much detail here. Another note I want to make here is that the count we're talking about here is supposed to be accurate count instead of an approximation of the count, such as the number of IP addresses and the unique requests from them. So now that we understand what the problem is, let's get started. Since we're a very small startup, all we do here is that I want to build something overnight so that next day we can just go start pitching our customers. It's just like building a plane during takeoff. So, and because we're building a database, we want all these nice properties such as being sharded, accurate, fault tolerant, etc. in our system. And to do all these things, we first started with a very simple solution. We call it version 0, which is just using Redis. And we divide our events into time buckets with expiry. And all of a sudden, we have a working database, which is very easy to use because Redis supports all kinds of common data structures. And doing integers countings in Redis is very simple. So let me give you a concrete example. Let's say at 4:10 p.m., we get an event from a particular IP. So we bucket that into a 15-minute bucket and increment the count for that key for that bucket in Redis, and we get a count. And then if at the same time we want to get the count for that key, it's very simple. For the hour, we just sum up the counts for the last 4 or 5 time buckets, and then we get the count for the IP in the last hour. So it looks like we're done. It's very simple counting. This is very easily shardable because there's a string key in Redis. We can have as many Redis shards as we want. And the problem is it's very expensive to do it because for a single count for the hour, we need 4 to 5 buckets to store it. And everything in Redis is stored in memory. It's very expensive. However, fortunately, when we first got started, we get a lot of free credits for the cloud infrastructure that we use for Google Cloud, Amazon, and as well as Azure. So we can afford a few expensive gears. That's why we get started from Redis. However, the key problem with this approach is that we're bucketing things into 15-minute buckets. It's not that accurate. And here's what we get. So it's not very accurate. It's kind of expensive. And we can back up Redis databases, but durability is still an issue because that is not very easy to do. And fault tolerance is still an issue. So, but we have something working that can show and demo to the real customers using a relatively small effort. Now we want to improve it in the next version, which enters Kafka. So the idea is that Kafka allows us to have a durable sequential log of messages. Why don't we just put the timestamped increments as Kafka messages? So what we have here is that we have a tuple of timestamp, a key, just like that. So at certain timestamp, we saw an IP and use that as key. So now, instead of having the clients doing both read and write directly with Redis, the clients only need to write to Kafka and read from Redis. And we have a separate Kafka consumer that reads this sequential log of messages, like timestamped keys, and does the increment. So let's say we see this key at 2:25 p.m. So we increment that key for the hour instead of having 15-minute buckets. And what's interesting here is that we can have a different Kafka consumer that's delayed by an hour. So an hour later, we can decrement the count for the same key. All of a sudden, now we can get the key for the hour anytime and have a relatively or much accurate count for that particular IP. And what's interesting about this approach is that we can extend it so that not only we can count keys by the hour, but also by the day by having another consumer that decrement the key a day later after we first saw the key. And we can even extend it further by having a week count or even month count. And because everything is persisted by Kafka, it's relatively easy to do. But the problem is you cannot persist Kafka forever. If we want to decrement a key for a month, we need to store up to a month worth of data, which is very expensive. Fortunately, what we can do is we can back Kafka messages to S3 and have another consumer that is consuming from S3 files instead of Kafka cluster by reading S3 files directly. As a result, we can have the week and month consumers that does the job without having Kafka persisting all the data. So as a result, now we have a accurate count system that is sharded using Kafka, and we can assign Redis shards to Kafka partitions, have a one-to-one mapping, which make it very easy to scale out. And it's also durable because the combination of Kafka and S3 can save all the data forever. But the problem is these things are still in RAM, which is still expensive to run, even though we have cloud credits. And these credits are expiring, so we need to find a way to reduce the cost so that eventually we can manage the cost for it using our own money. So now what we're looking at here is that we have three problems to solve. One, now that we're not writing directly to Redis, we need to find a way so that we have atomicity for our writes. And we need to manage the cost and fault tolerance. So atomicity is a relatively easy problem because when the increment fails before committing Kafka offset, we may potentially bump the count twice. And to solve this issue, we can combine these two operations in one Redis transaction by writing both the Kafka offset as well as the count itself using one transaction. And that gives us exactly one semantics. Now, we only need to solve the remaining two problems, cost and fault tolerance. Because Redis is something that is easy to first get started, but managing a large cluster of Redis is not only very expensive, but operational-wise, it costs us a lot of hours to get it fault-tolerant. And we need to manage the cost as all small startups. That enters version 2. So there are a few requirements here for us to build the next version of accounting database. First of all, we can no longer afford putting everything in RAM. So we need to put something on the disk. But at the same time, we want to manage the latency so that we still have pretty good tail latency when we read from the database. And finally, it's already our third time migrating data from existing database to a new version. So we want to make sure that migration is always easy and pain-free. That's our requirements. And we still want to maintain relatively accurate counts, because when we move from 50 million buckets to Kafka, we improve the count accuracy from up to 15 minutes of latency to just a few seconds. That's how we when Kafka consumer may potentially lag, but just up to a few seconds of latency. So there are a few things that we don't need to worry about here. One thing is very important, that is consistency. We don't need strong consistency here. That we need count. We don't need to count to be accurate by the milliseconds. Right? A few seconds of consistency, eventual consistency, is totally okay here. And second, we don't need to worry about magical sharding using consistent hashing, for example, and move data around. Having one Kafka partition correspond to one shard of your database is perfectly fine here for our purpose. Before we actually build our own database, we did use and considered at least a few alternatives like MySQL, React, and a few others. But unfortunately, they're either too expensive to run or are very hard to operationalize at our scale. So we decided that, let's build it ourselves. So that enters our current version of the database. So first of all, we still want to maintain the Redis protocol, because it's very easy to write a parser, very easy to write a client, and text-based, so that we can make a tooling very easy. But most importantly, because our clients already know how to talk to Redis, we want to keep that convenience for our next version of the database. And then instead of using the commercial databases, we decided that why don't we just replace each single Redis shard with an in-process database like RocksDB, which is open source by Facebook. It's very powerful, yet very tunable for different kind of workloads. And we still keep Kafka for durability and replication. And to achieve transactional support, we use the same idea by writing both the count itself and Kafka offset using the same transaction that is directly supported by RocksDB. And now we need to write a server. Since we are a small startup, why don't we just use the most cutting-edge language, which we did, and we prototyped our server using Rust. Unfortunately, it didn't work out for a few reasons. So eventually, we switched to C++ using a few other Facebook open source libraries to build our high-performance server. And mostly, it's because RocksDB is written in C++. So using the same language, we get support for direct binding compared to other languages. Now, we solved a few other problems. And what's remaining here is replication and fault tolerance. Kafka gave us replicated data log. However, the database itself is no longer replicated because when you use Redis, you can have Redis backups, not RocksDB. So we need to solve this problem. And the way we do it is using another cutting-edge technology, Kubernetes. And this time it's for real. When we first started, we decided to use Kubernetes when it was pretty much I would say a beta software, but we loved it. And the way we use it is that we can use Kubernetes to manage a set of containers that each would run a single shard of our database. And Kubernetes will make sure that we have a certain number of replications for our database. If certain host is taken down or failed, it would create new containers on new hosts automatically, make sure that we have the right number of replications. And an interesting problem here is that RocksDB is an in-process database that doesn't have any replication or anything. So we need to manage our own data replication. And moving data around is actually a relatively hard problem. However, we're living in the cloud age. Every major cloud providers have support for some sort of network-mounted data disks. For example, in Google Cloud, it's called persistent disks. So the idea here is that instead of moving data around, we can move disk around. So for each RocksDB partition that corresponds to a Kafka partition, we can write data instead of to a local disk. We assign a network-mounted disk to it. So when a certain host failed, Kubernetes will automatically create a new container on a new host by unmount the same disk from the previous host to the new one. So that way, we get data instantly to a new host that is well supported without worrying about copying data around. And the only time we need to copy data is when we want to increase the number of replicas to set up a new set of replicas. And doing that is also pretty straightforward because we can just take a snapshot of existing replica and copy it to a new set of network-mounted disks and start consuming from Kafka because, as we noted earlier, those disks and databases already have the next Kafka offset that we want to consume from. So as simple as that, we can start creating new replicas in a matter of few minutes. And a good feature about this replication scheme is that none of the replicas need to know the existence of other replicas because they read directly from Kafka. And as soon as the Kafka lag reaches 0, we claim that the new replica is ready to serve. Our benchmark, it takes just a few seconds to consume about, I think, 100K messages for each partition. So it's actually pretty fast in terms of getting a new replica ready for production use. And finally, we have a few replicas for the same partition, so we need to load balance the read across those replicas. And Kubernetes provides a very powerful feature called cluster IP. Basically, it creates a new IP address for each partition. And for the client, each client will run a proxy that is using IP tables to manage the replication across those replicas so that we don't need external load balancer for any of the databases that we run. The client only need to know one IP per partition. Now, we finally get to this place where we have all the nice properties that we want for our accounting database. And we built it using just a few off-the-shelf components that are open source and well supported. What's nice about this is that instead of just building this specific counting database, we built it as a framework as Smite. And then on top of that, we built a count capability using the framework. It just take 125 lines of custom code. We can get a counting database up and running on top of this framework. And what's nice about this framework is that now we can apply it to a lot of different problem domains inside Smite. For example, if we replace increment and decrement to set, all of a sudden we get, using the same idea, we get a key value store. And this key value store can not only support point queries, RocksDB has a very powerful feature to support prefix scanning so that we can do range queries in a very efficient manner. Another idea is that if we replace RocksDB or Redis in this schema and using Solr as the underlying storage, all of a sudden we can use Solr and Kafka together to build our own search engine using exactly the same idea. So that all sounds very nice, but there are a few problems that we encountered during the course. First of all, there's an engineer in our team that really loves Rust. That's how we get started building those databases. It's great language, manage the memory in a very innovative way that is, I think, is much better than C and C++. Unfortunately, since we heavily rely on RocksDB, we want a C++-based direct binding to it. So we have to give that up and use C++. Another issue is that it's not fun combining the latest Docker version and the latest Kubernetes and make them work together. With a lot of production issues, including temporary data loss because certain versions of these two software that doesn't work well together, and we were not aware of that. Another issue is using the Kubernetes-based network-mounted disk is a great idea, and we still love it. However, it takes much longer than we expected to actually launch a new disk from a new host. You would think, in a few seconds you can move a disk around, but in reality, it takes about a minute, which is something that we really want to improve. Another issue is because we're writing to Kafka and reading from RocksDB, we cannot guarantee read your own write. So we want to improve that as well. One idea is that when you read, what you have is a Kafka offset. So instead of reading directly, we can ask the database, hey, don't return any results until you caught up to at least to this offset. Then we can guarantee the same read for the write that we gave just a few seconds ago. So there are some future work that we're considering using the same framework. First of all, as I mentioned earlier, a different type of counting problem is called unique count. And there's a well-known set of algorithms called sliding hyper or hyperlog to solve this problem. But we can apply, what's interesting is that we can apply this same framework and principle here and build the same unique count database. And we recently have that running in production, and we're thinking of open source it because it turns out that there are a lot of different scenarios where we can apply these awesome algorithms in production environment. Another interesting technology we're looking at is Kafka Streaming, which just came out, I think, a few months ago as a beta version software. The reason why we're interested is because, as you can see, we built our technology mostly based on Kafka and RocksDB, which is exactly how Kafka Streaming is based on. So we think we share a lot of similarities, and maybe we can combine these two approaches, have a more scalable solution to our system. All right, that's the end of my talk. Thanks for listening. For your time.
If there are any questions?
Sure.
So I missed part of your talk. Sorry, I came in late. Between version 1 and version 2, you replaced Redis with Rocks?
Yeah. So the question is, yes. So we between version 1 and version 2, instead of using Redis, we use in-process database, and Redis is our RocksDB is our choice. Yes.
I missed the beginning. So is this code going to be open source?
Yeah. So the question is, can we open source this code base? Yes, we are actually considering open source our framework based on C++. Yeah.
So the other question is that you designed this for your use cases. Is this database used for general use cases other than specific?
So yeah, the question is this approach generalizable to other use cases? And we believe, actually, as I mentioned earlier, after we built our database, we found that the same principle can be simply applied to other domains, of course, inside our own team. But we believe the same idea, using Kafka for replication and RocksDB for storage can be applied to many other problems. And it's a relatively cheap way to build replicated distributed database without too much knowledge about distributed systems.
Maybe one more question, sir.
Sure.
I know the Netflix DB cache team also does similar things using RockDB, but I don't think it uses memcached. They do the similar type of thing. Are you aware, the differences or same similarities?
Actually, I'm not aware. So you said Netflix is an open source project.
Yeah,
EB cache.
Yeah, so we're going to give a talk at one of our meetups.
Oh, definitely, I want to check that out. But based on name, I would say that's a technology based on caching instead of have persistent storage of data.
They're using RockDB underneath as well.
I see. Definitely want to check that out. Thank you. Yes.
In the Kafka stream is kind of not 3 months, 4 months old. It's probably over 1 year. So you never really considered to look into Kafka streaming. Sorry, not the Kafka streaming, Spark streaming.
Spark streaming. So I think we're solving. So Spark streaming is it's definitely something that we considered, but the problem is it requires us to run a different set of frameworks. So that's why we would like to check out Kafka streaming, which is more of a library than a framework that is less intrusive, and we can maybe incorporate that in, directly into our own system. Yes.
Talk about the greater pipeline. We talk about the algorithm used for like detecting anomalies.
Mm-hmm. Sure. What's your question? Sorry.
Talk about your algorithm. What kind of how do you detect anomalies?
I see. So, yeah. So, yeah, definitely. So the question is, can we talk about some of the algorithm that we use for detection? It's actually a very interesting question. So the way we build systems at Smite is that we try to build a developed platform, and what that means is instead of saying, "Hey, give me your data, and we give you the results of yes or no, right or wrong." We build a platform so that it has individual building blocks for detection, and you can use them yourself. And we even give you a GitHub so that you can customize the behavior. So what that means in practice is that, for example, I have this counting database that the counts of IPs and signups and domain names give me the signals. And we can provide a unsupervised learning algorithm as a building block for you to know if certain IPs or certain email domains have a bad reputation. And you get this reputation results, and you can decide whether or not this is something that you need to look into. And the same, building on top of that, we have mostly unsupervised learning models about the detection of bad users, for example. Say, hey, if the user has a lot of signups, is coming from an IP or email domain or ISP that we don't trust because of other reputation data, then we can decide maybe it is something that you need to either automatically bad or something that people can look into manually. So I think my point here is that we don't dictate on a specific algorithm that we use, but provide all these information and data as a building block for you to either work with us to come up with the rules and models, or you can customize yourself.
Are you doing it in batch or streaming?
So we actually support both. So you can call us using a synchronous API like streaming, and we'll give you results directly. But that because the synchronous, that comes with a latency budget. So we may not run through all the detection and classification algorithms. But if you give us messages in batch, we may not give you answer directly, but it takes a few seconds for us to run through all the algorithm that we have. Then we can give you answer back using a webhook. That way we can have more accurate results, but at the cost of a few seconds of latency.
I would like to ask a question.
Sure.
Since you work with computational linguists, because for fraud detection you have to use computational linguistics.
Yes.
Is it difficult to, like, you filled your data structures with numbers, and that's easy.
Mm-hmm.
Is it more difficult for you to fill the same containers with words instead of numbers?
Yeah.
Isn't it better? I mean, you have a knowledge base, you have a database
Mm-hmm.
of something.
Yeah, exactly. So the way we look at it, this problem is that we want to provide the building blocks for our customers. Mm-hmm. So we take off-the-shelf NLP algorithms and look at the text that people send us. Say, hey, is this message bad because it contains harassment or spam?
Yes.
And we assign a score to it, which we call reputation.
Okay.
And then people who use our system can take that result. Right? They can either say, hey, we don't allow any harassment or spam messages in our system. So as soon as we see a score above a certain value, we want to classify it automatically as bad. So they take that results.
So it's not just detect the problem, you also offer a solution.
Yes.
Same package.
Right.
That's very cool.
Thank you. Cool. All right, thank you.